then because the bandwidth is B here, all right, double sideband, so therefore I have here my lower sideband, I have here my upper sideband. All right, so this will be FC plus B, so this will be FC minus B. All right, and same thing here, if I were to shift this entire spectrum to center at minus FC, so I'm going to get this here. All right, so this is minus FC plus B, this is minus FC minus B. Okay, so what is the bandwidth? So in this case, you can see the bandwidth. Again, the bandwidth, I take the highest frequency in the signal minus the lowest frequency in the signal. All right, that means it's FC plus B minus FC minus B. All right, so that will give me a bandwidth of 2B. Okay, so this is the double sideband suppressed carrier signal. Again, you can see we don't have anything at FC. Okay, we don't have a component at the carrier frequency. So therefore, there is a double sideband suppressed carrier AM signal. Okay. You got this down?
Oh, yes, we got this down.
Yes.
Okay, I move on. Now, let's go through an example. We have a AM. Wait, double sideband. Oh no, let me make a correction here. Double sideband. Yeah, okay. Typing error. Double sideband suppressed carrier. Can you make a correction, please? Double sideband suppressed carrier. Okay, double sideband suppressed carrier modulator with a carrier frequency FC being 200 kilohertz and a modulating signal frequency of 10 kilohertz. All right, you are asked to determine the lower sideband and upper sideband frequencies, then the bandwidth, and also the output frequency spectrum, indicating the lower sideband and the upper sideband. Okay, so now let's calculate the lower sideband. The lower sideband frequency F subscript LSB is equals to FC minus FM, right? From here. The lower sideband frequency is FC minus FM, right? The upper sideband frequency is the FC plus FM. All right, so we'll calculate based on this. And where do I get this from? From here, from this equation. Yeah. So that will give us 200 kilohertz plus 10 kilohertz. No, plus minus. Minus. So this is minus. You can do it on your own faster. I write very slow. So that will give me 190 kilohertz. All right. And the upper sideband frequency will be equals to FC plus FM. And that is 200K plus 10K. That will be 210 kilohertz. Okay. Then B, which is the bandwidth. We know that bandwidth is actually 2 FM. All right, and that will give us 2 times. I write slower than my brain, so therefore I move on to talk. I want to straight away write 20 kilohertz. Okay, let's get back here, and this is 10K, and bandwidth is 20 kilohertz. Okay. You can also find the bandwidth by taking the upper sideband frequency minus the lower sideband frequency. Okay, and that will give you 210 kilohertz minus 190 kilohertz. All right, which will give you the same answer as 20 kilohertz. All right, so very simple maths. Let's draw the output frequency spectrum. So, why I go to C block? This one should D block. This should be C. Okay, C, the output frequency spectrum. So we have, as far as the frequency spectrum is concerned, because this is double sideband suppressed carrier, therefore you have, now I have, this is 200. This is frequency in kilohertz. All right, so I have 200, I have minus 200, and I have 190. This is 190, not to scale. 210. This is minus 190. This is minus 210. All right, therefore I have here 2 impulses. Modulating signal frequency. So my modulating signal is a single frequency signal. All right, single frequency signal, therefore you get only the 2 pulses, 2 impulses. And then I have another set here. All right, so this question never mentioned what is the amplitude of the signal, so therefore you can leave the amplitude blank. Here you need to indicate where the lower sideband and where the upper sideband is. So again, the lower frequency one is this is 0. The lower frequency one is a lower sideband. The higher frequency one is the upper sideband. This is upper sideband. Okay, and this is amplitude. Okay, so all these 4 sidebands have equal amplitude. Yeah, have equal amplitude. Again, this is we are getting this from the equation previously. This equation here, our lower sideband and our sideband has the same amplitude of BMBC over 2. Okay. Did you get this now as well?
Yes. Yeah. Yes.
All right.
Yes, we can.
All right, let's move on. So example 2. If I have a voice signal with a band of frequency from 0 to 4 kilohertz, transmitted using a carrier of 500 kilohertz, determine the following of the modulated signal: so bandwidth and as well as the output frequency spectrum. All right, so what this means is I have a signal with band frequency 0 to 4 kilohertz. That means is as far as my baseband signal is concerned, all right, I have 0 to 4 kilohertz. So that means the baseband, I have 0 all the way up to 4 kilohertz. This is my voice signal. So again, I'm going to assume flat lah. That means the amplitude for all the frequency are the same. It can be of any shape. Here, just for simplicity, I make them the same. So that means I have span from 4K to minus 4K. If I plot on both sides. Okay, so my carrier is 500 kilohertz. So that means the bandwidth. Let's talk about bandwidth first. Bandwidth, again, if you refer back to the previous slides, the bandwidth of here is actually 2B. All right, if I have my baseband signal that span over a range of frequencies, all right, so I mean the highest frequency is B here. Right, that means the bandwidth will be 2B. Yeah, so in this case, my highest frequency is 4K. Right, So my bandwidth will be 2B, and this is equals to 2 times 4K, and that is actually 8 kilohertz. Okay, and then B, the output signal spectrum. Okay, the output signal spectrum, this is my baseband, and now I have again, this example is on double sideband suppressed carrier lah, since we are on that topic now. So that means okay, now I have FC, again not to scale. Okay, this is minus FC. So what happened is this entire spectrum will be shifted onto here, so that it's centered at FC. Instead of centered at 0, it will be centered at FC. So that means I have like that. Okay, so this will be FC plus 4K, and this will be FC minus 4K. All right, so same thing on this side, it will center here at minus FC. All right, so this is okay, let's put it in numbers. Let's put it in numbers, don't write FC lah. Okay, since I know what is FC, okay, so here my FC is 500 kilohertz. All right, so that means this is 500 F in kilohertz. All right, so this is 500 kilohertz, and my highest frequency in my voice signal is 4K, so that means this is 504. All right, and then minus 4 will be 496, isn't it? Yeah, and then same thing here on this side, this is minus 500, so this will be minus 496, and this will be minus 504. Okay, so if you have some problem handling negative numbers, then I'll suggest that you always draw the positive frequency first. Then on the negative side, it's just a reflection. All right, it's just a mirror reflection on the negative side. So 496 minus 496, 504 minus 504. Okay, so this is amplitude. Amplitude is always invoked. Okay, so this is for 0 frequency. Okay. Easy? Hello? Have you taken this down? Then I'm move on already.
Yes.
Okay, good. The next one is on the, we're going to talk about the modulator. All right, how we actually generate the double sideband suppressed carrier signal. So we know that to generate a double sideband suppressed carrier signal, mathematically it's very easy. You just multiply the two signals together. All right, you just multiply the signal together. Therefore, you can straight away make use of the multiplier. All right, buy a multiplier, and then you actually use that to put the two signal in as an input, and then your output will be the double sideband suppressed carrier signal. But we can also make use of non-linear modulators. Okay, and with that, then you can also generate your double sideband suppressed carrier signal. Okay, so I won't go into the details, so you can go through the maths if you like. Yeah, and let's move on. You can also use switching modulators. Actually, if you look at the amplitude modulated signal, all right, the amplitude modulated signal is actually very, very similar to the the switch version of the carrier signal. You just switch the carrier on and off, and then where the amplitude actually following the message itself. All right. Therefore, you can actually do that. You can do that by generate the double sideband suppressed carrier signal by using switching modulators. All right. So in the time domain, all right, in the time domain, you can generate this signal by actually, if you look at it, it's like multiplying these two signals together. All right. So let's say my message has a baseband spectrum that look like this. Okay, and then the carrier signal, for as far as this is a series of rectangular pulses. So the Fourier transform for rectangular pulses are actually a spectrum of, you actually have impulses that actually going to take a sync shape. The envelope will be sync shape. All right. So now if you were to multiply these two in time domain, so in frequency domain, basically what you're doing is you're shifting this spectrum to all the uh, frequencies where we have the impulses. All right, so you can see that the envelope of this signal will be take the sync shape. All right, but then you will have the spectrum of the message centered at all the what do you call that, the impulse frequency. Okay, and the magnitude actually will slowly will be diminishing yeah, as the frequency increase. And I'm going to get this signal. Again, this signal, because if you look at the signal, is actually is a form of rectangular pulses, except the amplitude is different. It's changing according to the amplitude of the message signal. You can see that in the frequency spectrum, you are going to have a lot of components at high frequencies. All right. So we don't really want the component at high frequency. We just want the component at the carrier frequency, which is these two. All right. We also don't want this baseband because this baseband cannot be transmitted. All right. So what we do is we actually pass the signal through a bandpass filter. So a bandpass filter basically will actually allow this signal at omega c to pass through. All right, these two to pass through, and this will be our double sideband suppressed carrier signal. Okay. So as far as the filtering is concerned, after we pass the signal through a bandpass filter, you can see that this signal, okay, will actually take this shape, okay, take this form, and this is your double sideband suppressed carrier signal. All right. So what it means is, if you look at the signal itself, all right, the carrier now has the high frequency. We have a series of high frequency signal, which is at the carrier frequency, and then the envelope again, the amplitude of the carrier signal at different time actually following the amplitude of the message here. Okay, so you can see that the envelope actually follow. All right, what we get rid of is the high frequency component here at the sharp transition here. We don't really want this sharp transition. The frequency is too high for the system to respond, and we don't really want this high frequency. Okay, we want to transmit our signal at omega c only. Okay, as far as the maths is concerned, right, because we multiply these two signals, so we're going to multiply the MT with the WT. WT basically is the Fourier series expansion for rectangular pulses. All right, Fourier series expansion for rectangular pulses basically is the fundamental frequency, all right, and also followed by all the odd harmonics. All right. Again, we are not interested in all the harmonics. We just want the fundamental frequency here. So therefore, by passing this signal through a bandpass filter, we actually get this signal at the output, which is our double sideband suppressed carrier signal. Okay, so that is for switching modulators. All right, you can also use Diode Bridge All right, we make use of a series of diode bridge. You can put it in series mode or in shunt bridge mode. Yeah, either one will actually again give you the double sideband suppressed carrier signal after you pass the signal through a band pass filter. It's very similar to the concept of the switching modulators as well. So you get this. All right, after the band pass filter, you get the multiplied version or the product of this message with the carrier here. All right, except that the amplitude is being changed by 4 over pi. Yeah, but again, this is a constant, so therefore you actually preserve the amplitude of the original signal. Okay, that is so much about modulation. All right, so what about demodulation? We want to recover our signal. I think I talk about this in our next lecture lah. Okay, I talk about this in the next lecture because that is quite lengthy, so I don't think I can finish. I have about 15 minutes left, right? So I want to keep this for next lecture. I have a question for you just to check your understanding. Um, okay. So you may want to go through the notes first while I set up the question in Google Classroom. You should be able to see the question now in Google Classroom. Can you?
Yes.
Okay. So I give you 5 minutes to answer. I can see that 7 students still haven't answered the question. So I don't know whether it's because you are still thinking or you are not with me. All right, now drop to 5 already. That means 2 has answered. So the other 5, quickly pick an answer lah. It's not actually a test, you know. Actually, if you actually follow my lecture, the answer is very, very straightforward. Okay. The rest are just smoke to confuse you. That's all. If you know the answer straight away, you get to the answer. Okay. All right. So quickly, if you actually go through the lecture notes, you'll find that the bandwidth of a double sideband suppressed carrier signal of modulating signal bandwidth B, all right, and the carrier frequency F is actually 2B, right? Because the carrier frequency has no effect on the bandwidth of the modulated signal. Yeah, what we did actually, we just shift the entire spectrum of the modulating signal frequency to center at carrier frequency. That's all. All right. And because it's a double sideband modulation technique, therefore the bandwidth now become double lah. All right, so it become 2B. Okay, so majority got it right, which is good. Okay, so the other 3, I think there are 3 students who got it wrong. Okay, so hello, this course there are many equations, you know. So with this first few equation, they are very, very straightforward. You have to make sure you know it well first, or else when other equation comes in, you will be confused already. That's a problem with some of the students who actually failed this course before. All right, when we actually cover the entire course, there are many equations involved. So they kind of mix up already. What's this equation for? What's the equation for? What's the equation for this? What's the equation for that? So if they use the wrong equation, even though the question actually is very, very simple, wrong equation meaning wrong answer. Okay. All right. So that okay, that should end the class today. But before I end, let me bring you to your tutorial. Okay, so basically I have uploaded tutorial 2 questions, all right, in Google Classroom. So you should be able to do question 1 and 2, maybe part of 2 lah. All right, but question 1 definitely you can do it already. It's just that, okay, let me share my screen with you. Window, share this screen. Okay, can you see my screen now?
Yes.
Okay, so this is a screen showing tutorial 2, which cover amplitude modulation. There is no tutorial for chapter 2, or chapter 2 is just a revision in it. So for this question 1, all right, question 1, you just need to be a bit careful on the expression here, because MT is cos 1000 T. So 1000 T, so this 1000 is actually omega. This 1000 is your omega, it's not F. All right. Omega is equal to 2 pi F. All right, 2 pi F. So cos of omega T. All right, so here is T given, and then for this 1000 is in omega. All right. So when you have an expression in omega, then you have a choice of whether you want to plot the frequency spectrum in omega, or you can plot it in F. If you want to plot it in the linear frequency F, then you need to convert this 1000, which is omega, into F first. All right, by using the relationship omega equals to 2 pi F. Okay. And also, if you refer to the references, I think I put it here, right? Yeah, okay, the appendix. So this is a useful information for you. So as far as the appendix is concerned, this is standard appendix. You have appendix A, B, C, and D, but for this course right now, for this chapter, you're going to use, you can actually make use of the table of Fourier transform, appendix B. You actually show you here what is the Fourier transform for cosine wave, all right, a cosine signal in F and in omega. All right, what I've shown you just now is in F. Basically, when you perform Fourier transform on a cosine signal, all right, you get two impulses, all right, one at f0, one at minus f0, right? So what happened here is your delta function, remember delta function? Delta function, the amplitude is 1 when the term in the bracket is 0, right? So this term, when when is the condition for this term to be 0? This term will be 0 when f equals to f naught, isn't it? Yeah. Therefore, you have a magnitude of half. All right. An impulse with a magnitude of half when f is equal to f naught. And you also will have another impulse when this term in the bracket is 0. So that means your f is equal to minus f0. Yeah, when your f is equal to minus f0, this term in the bracket will be 0. Delta 0 again will give you a magnitude of 1. You multiply by half, you get your impulse with the magnitude half. And this half is when your cosine signal again has an amplitude of 1. All right. This one is not written here, but it's understood, isn't it? In maths, there's a 1 here. So your amplitude will be half of it. And if you were to plot the spectrum in omega instead of f, all right, so what will happen to your impulses is you have, again, two impulses. One at omega equals to omega naught, the other one at omega equals to minus omega naught. All right. And then the magnitude will be multiplied by pi. All right, if it's 1, then it's pi. If it's 2, then it will be 2 pi, and so on. All right, so you make use of this table to actually plot your spectrum. And then appendix C basically has contained the table of trigonometry relationship. So we're going to use, if you cannot remember the identity from your maths, then you can always make use of this table. All right, these are the equations that we're going to use in this course. Okay, so the one that I mentioned just now is this. The 2 cos x cos y is here. All right, so you have a sinusoidal signal, then again will be cos minus x, x minus y, again cos x plus y. Again, you have two terms here. All right, so as far as the signal is sinusoidal, then you always have a terms of x minus y and x plus y as a result. Okay, so you can actually do your tutorial already. All right, so it's going to take some time for you to plot. So I hope you can actually try to do this on your own. All right, for the coming tutorial session, I'll just show you, I won't show you all, I'll show you maybe one or two. All right, and then we move on. Yeah. So don't expect me to give you the all the solutions for all the questions in tutorial. Yeah. You actually have to try it yourself. And then if you have problem, then we discuss. Is that all right?
Okay, understood.
Yeah, good. I mean that will actually benefit you in the long run, yeah. So instead of me giving you all the answer and then you never get the chance to practice. Okay, so that should end the class for today. I'll see you next time then.